The question that I have is, could you discuss the stress strain and strength behavior of normally consolidated clay during triaxial CD testing? CD here stands for consolidated drain testing. So let's go ahead and start our discussions. First with the behavior of normally consolidated specimens during triaxial CD tests. Everybody remembers what CD stands for? C for consolidated, D for drained, right? So there will be no pore water pressure in the specimen during the either the consolidation or the shearing phase of this triaxial test. And therefore sigma 1 prime equals sigma 1, sigma 3 prime equals sigma 3. I'm going to be plotting the stress paths in the PQ space, so let's remind ourselves of the definitions of P and Q. In fact, I'm going to be plotting typical results in three different spaces. PQ space, Q epsilon 1 space, where epsilon 1 is the vertical strain, and then finally white ratio versus P prime space. Let's say this is my virgin compression curve. Just like we have plotted the virgin compression curve with respect to one-dimensional consolidation test where we plotted E against sigma V prime, we can do the same thing here. Here we plot E against P prime and there is a virgin compression curve in that space. The initial state of a normally consolidated specimen will lie on that virgin compression curve. I'm going to plot typical results for three different tests. In test number 1, I'm normally consolidating my specimen to a confining pressure of P naught prime, and then I'm going to shear it. Of course, here we are talking about CD test, right? And therefore the shearing is going to be done in a standard triaxial manner, but under drain condition. I have plotted typical results in all three spaces. In the PQ space, the stress path is a straight line with a slope of 3 vertical to 1 horizontal, and the specimen fails at this point. In the Q epsilon 1 space, we get a nice smooth hardening curve like this. No strain softening here. In the EP prime space, the path looks something like this. It fails over here. Here are the results of my other two tests. Test 2 is conducted with the confining pressure of P02 prime and it fails over here. Test 3 is conducted with an initial confining pressure of P03 prime and it fails over here. The stress strain curves are similar. They are basically hardening type. And I have also shown the paths in the EP prime space. Now you wonder if there's a pattern here, right? See what happens. If I connect these 3 points, the failure point, we get a nice straight line that passes through 0. On average, of course, accounting for experimental errors. Now I come over to the EP prime space and connect these 3 points. They fall on a very nice smooth curve. This line right here is called the critical state line, CSL for short. This line right here is also called critical state line. You could think of this as the projection of the critical state line in the PQ space onto the EP space. For emphasis, we could call this a critical state line in the EP prime space. So here I have summarized the important observations, some of which we have already talked about, the others we haven't. So let's just go through. So in the PQ space, the failure points lie on a single straight line passing through 0, which we call critical state line. The stress strain curves are all hardening type. There's no strain softening on them. In the EP prime space, all the failure points lie on a single smooth curve, and also we see that the white ratio decreases in all three tests. In other words, the specimen experiences a volume decrease or compaction. Next question is there a more practical result that come out of it? The answer is yes. Here it is. Well, what did I do here? Well, I took the failure stresses sigma 1 F prime and sigma 3 F prime at this point from test number 1, right? And I constructed this Mohr circle. Okay, so this will be sigma 1 F prime and this will be sigma 3 F prime. And I did the same from the results of the other two tests. So here is the Mohr circle corresponding to test number 2, and here is the Mohr circle corresponding to test number 3. Now I try to draw a failure line to be tangent to all three circles, right? So it turns out approximately that failure line passes through 0. So what does that mean? Well, cohesion is 0. We do have a friction angle, which is the slope of this line, but there's no cohesion. Remember, we've been saying that the normally consolidated clays don't show any cohesion? Well, here is the proof. Is there a connection between the failure line in the PQ space and the failure line in the Mohr Coulomb space? The answer is yes. You can actually prove that if this line, the failure line in the PQ space passes through 0, the failure line in the tau sigma space is also going to pass through 0. I will not get into the proof here, but it's a useful observation because when we start talking about over-consolidated clay, we're going to see that the failure line is not going to pass through 0 in the PQ space. It's going to be something like that, right? There's going to be an intercept over here, and then we will find that there is going to be an intercept in the tau sigma space as well, and that's what gives you cohesion for an over-consolidated clay.